Hello and welcome to the second FMSP Core Prerequisites video. These videos are designed to help you get ahead with independent study of the A2 core, ready to develop the skills in A2 further pure modules. This shows what you should already know. If you're not sure about all of this, particularly the two marked with an asterisk, then work through video A1 first. It's a good idea to have these things to hand as you work through the video, so pause the recording now and go and get everything together. Make sure you've set aside sufficient time to tackle the questions as well as watching the video. We've just one topic in this video, the trigonometric addition formulae. We're going to start by deriving them using this diagram. We're going to work out an expression for sine of a plus b in terms of sine a, sine b, cos A and cos B. Look at triangle OPQ. You'll see that OQ is marked with length 1, and that means that OP is equal to 1 cos B. Now look at triangle OPR. We've seen that length OP is equal to cos B, and therefore RP is going to be cos B, the hypotenuse, times sine A. Now look back at triangle OPQ again. We want to find the length PQ, and that is equal to 1 sine B. Now look at triangle PQT. We've just found length PQ, that's equal to sine B. The angle at T is a right angle, and the angle at P is the same as angle A. That means that length PT is equal to sine B, the hypotenuse, cos A. Pause the recording to check you agree with all of these. Now we can look at length QH. You'll see from the diagram that QH is the same as RT and is therefore RP plus PT. We've found both of these lengths already. The angle at H is a right angle, and if we look at triangle OQH with hypotenuse OQ, which is equal to 1, you'll see that QH is equal to sine of A plus B. RP, we've already worked out, is cos B sine A, which I'll just write the other way round, sine A cos B. And PT is equal to sine B cos A. And there is the first of our addition formulae. Sine of A plus B is equal to sine A cos B plus sine B cos A. Now we're going to find an expression for cos of A plus B. You might want to pause the recording now and try it for yourself. I'll give a hint next before going through it. Okay, so if you're trying to do this on your own but you want a hint, then you should note that cos of A plus B is the length OH. So that's the hint. So if you think you can do it yourself now, pause the video and have a go before you watch me do it. Okay, so to check your work, or if you weren't sure what to do, here's the derivation. The length OR, we already worked out on the other video that OP is equal to cos B. This is a right angle down here at R. So looking at triangle OPR, we can see that OR is equal to cos B, the hypotenuse, cos A. QT at the top of the diagram, we're going to use triangle PTQ again, which from the previous slide, we'd worked out that PQ was equal to sine B and noted that the angle at P was equal to A. And therefore QT is equal to the hypotenuse sine B times sine A. And if you look at the diagram, you'll see that we've got plenty of right angles in here, and HR is the same as QT. So the length that I said we wanted was OH, and that is equal to OR take away HR, and therefore OH being cos of A plus B, using the triangle OHQ, is equal to OR, which we've worked out was cos B cos A. I'll just write that the other way round. Take away HR, which is the same as QT, which is sine B sine A. I'll write that the other way round as well. And there is our second addition formula. If we replace B with minus B, then we can get two new versions of this. You'll remember that cos of minus B is the same as cos of B, so there we'll have sine A cos B, whereas sine of minus B is minus sine of B, so that will give us a minus sign, minus cos A sine B. For cos of A minus B, again, cos of minus B is the same as cos of B, so the first term doesn't change. And sine of minus B is minus sine of B, which changes that minus sign into a plus sign. These formulae are both in your formula books, in both versions with plus and minus. Note that the cos one, we've got that minus plus sign there. Pause the video and find this formula in your formula book now so that you know where it is. Okay, some common variants. Sine of 2A is sine A cos A plus cos A sine A. So that means it's just two lots of sine A cos A. And cos 2A is cos A minus sine A sine A, or cos squared A minus sine squared A. These are easy to work out, but they're also very easy to remember, so you probably won't need to work them out. There are a couple of extra versions of the form for cos of 2A, which are extremely important in calculus work, and that's why you need to know this topic before you move on in further pure 2. We'll look at deriving both of these. We're starting with cos 2A equals cos squared A minus sine squared A from the previous slide, and we're going to replace the sine squared A with 1 minus cos squared A from that Pythagorean identity that you know from AS. Simplifying that gives us two lots of cos squared A minus 1. Similarly, we can replace the cos squared A with 1 minus sine squared A. And that gives us another version, which is 1 minus 2 sine squared A. Now it's very easy to half remember these, but rather harder to remember which way round they go. So you have a choice. You either need to learn them, or you need to remember that they exist and be able to derive them quickly. Well, why do you need to know these? Let's have a look at some examples. This might be typical of an exam question, and you're asked to prove that one thing equals something else. It's always a good idea when faced with these to try, for starters, the more complex side, because it's easier to simplify something complicated than it is to work out how to make something simple more complicated, because there are lots of ways of doing that. The bit in brackets is there to satisfy the pedants, and of course as mathematicians you're probably naturally pedantic. It just means that we're not dividing by 0. You don't need to really worry about that. It's just there to cover the exam board about the fact that we need to note that a is not a multiple of pi, otherwise it's not going to work. Okay, so we're going to start with the left-hand side. What to do? Well, start by the only thing you can do, which is to rewrite both tan and sec in terms of sine and cos. So that's tan, and we're dividing by sec a minus 1. And sec is 1 over cos, so that's 1 over cos a, take away 1. Now that looks really horrible, but it's fairly obvious what you need to do to it. We need to tidy it up and make it look nicer. So we'll start with a bracket and put that over a common denominator. So we'll have a common denominator of cos a, and then that's 1 minus cos a. Then we're dividing by a fraction, so we turn it upside down and multiply. So that should have been a small a. And then you'll see that the cos a's cancel, and we're left with sine a over 1 minus cos a. Now that looks quite simple, but it's not what we're aiming for. So we go back and we have a look at what we're aiming for, and you will see that I've got half a as the input. So I need to change these using the double angle formulae. So you'll maybe remember from previous slides that we had sine of 2a was equal to 2 sine a cos a. So I can replace my sine a with 2 sine a half a cos a half a. And cos of 2a is equal to cos squared a minus sine squared a. That's the easy one to remember, and we want it in terms of sine, so that's 1 minus 2 sine squared a. So 1 minus cos a is 1 minus 2 sine squared a half a. And that's equal to 2 sine a half a cos a half a, all over 1 minus 1 is nothing, and then take away minus, so 2 sine squared a half a. So the 2's cancel, and the sine half a on the top cancels with one of the sine half a's on the bottom, giving us cos a half a over sine a half a, which is cot a half a, as required. Now the only slightly not obvious step was whether we were going to change the cos 2a to 1 minus sine squared, 2 sine squared a, or 2 cos squared a minus 1. And sometimes you just have to try one, and if it doesn't work you need to try the other if you can't see that you need sines on the bottom in order to get your cotan. Okay, here's another use for these in solving equations. I've got sine 2x and cos x, so I've got two different inputs, and we want to change to using the same input. So we'll change the sine 2x to 2 sine x cos x. Now the really important thing here, don't divide through by cos x. That's because cos x might be 0. And dividing by cos x will mean you'll lose the solution where cos of x is equal to 0. You won't get an impossible situation, but you will lose a solution, and that will lose you marks in the exam. So instead of dividing by cos x, I'm going to subtract cos x from both sides. And then I can take cos x out as a factor. And then I can deal with the case when it equals 1 separately. So now I've got the two possibilities that either cos of x equals 0 or 2 sine x minus 1 is 0. In other words, sine x is a half. And that gives me x is 90 degrees or 270 degrees from cos of x being 0, or 30 degrees or 150 degrees from sine x being equal to a half. Okay, here's one for you to try. Pause the video and try this one by yourself before listening to the solution. Okay, if you've had a go yourself, here's the solution. We've got the expression cos 3 theta cos theta minus sine 3 theta sine theta. Well, that looks to me like cos A cos B minus sine A sine B. So that must be equal to cos of A plus B. So cos of 3 theta plus theta, which is cos of 4 theta. So that's answer D. Here's another identity that's rather useful. Tan A plus B. We know that tan is equal to sine over cos, so tan of A plus B must be equal to sine A plus B over cos A plus B. We can use the addition formulae that we've already worked out. So sine of A plus B is sine A cos B plus sine B cos A, and cos of A plus B is cos A cos B minus sine A sine B. Now, it may not be obvious what we can do to make this nicer. This is a little bit of a trick. Somebody thought, oh, what happens if you do this, and found that it all falls out rather nicely. If I divide top and bottom there by cos B, then the first term on the top becomes sine A. The second term on the top, I've got sine B I've got sine B divided by cos B. That's tan B. And I've still got the cos A. And dividing the denominator by cos B, the first term will just be cos A. And then I've got sine A, and sine B over cos B is tan B. Now I can divide everything by cos A. So the first term is now sine A over cos A, which is tan A. And the second term, I've got tan B, cos A divided by cos A. And then in the denominator, cos A divided by cos A is 1. And sine A divided by cos A is tan A, and I've got tan B. So there is an identity for tan of A plus B. It's tan of A plus tan of B over 1 minus tan A tan B. In the formula book, you'll find it written out with the option of a minus sign. So tan of A plus or minus B is tan of A plus or minus tan of B. all over 1 and then minus plus, so the opposite way round, tan A, tan B. It's a useful exercise to see what happens if you try starting with tan of A minus B and seeing if you can get that version of the formula. Okay, here's another one for you to try. Pause the video and have a go yourself. You'll need to use the identity that we had from the previous page, so I'll just write that up here so that you've got it handy. So you can pause the video now and have a go at this question. Okay, let's have a look at the solution. So we're starting with tan 2 theta equals 3 tan theta. We first of all need to apply the identity. So tan of 2 theta, that's tan of theta plus theta, so that will be tan theta plus tan theta, or 2 tan theta on the top, and 1 minus tan theta, or 1 minus tan squared theta as the denominator. Okay, I've got fractions. It's always a good idea to get rid of those as soon as you can, so multiply through by 1 minus tan squared theta to get 2 tan theta equals 3 tan theta minus 3 tan cubed theta. This is going to need factorising, so let's get everything on one side and set it equal to 0. 3 tan cubed theta minus tan theta equals 0. And then, again, as before, don't divide by tan theta because you'll lose the solution when tan theta is 0. Take it out as a factor, tan theta brackets 3 tan squared theta minus 1 equals 0. And that gives us that either tan theta is 0 or tan theta is plus or minus 1 over root 3, depending on which of those brackets is 0. And from those we get 4 solutions. If tan theta is 0, we're looking at theta being 0 or pi. And if tan theta is plus or minus 1 over root 3, we'll get pi over 6 and 5 pi over 6. We know this time that we need our answers in radians because we're told that theta is between 0 and pi. Okay, one more for you to have a go at. Pause the video and try this yourself first. Right, here's the solution then. Cos of 2 theta equals sine theta. We'll use 1 minus 2 sine squared theta so that I've got all sines rather than a mix of sines and cos. So 1 minus 2 sine squared theta is sine theta. And then get everything on one side of the equation. I'm going to collect on the left hand side but then swap them round, so that'll be 2 sine squared theta plus sine theta minus 1 equals 0. This is a quadratic equation in sine theta, and you might prefer to write it as 2s squared plus s minus 1 before you factorise it, but otherwise you'll get this 2 sine theta minus 1 sine theta plus 1. And that gives us two options, either sine theta equals a half or sine theta equals minus 1. And from that we get that theta is either pi over 6, 5 pi over 6 from theta being a half, or theta being minus 1, 3 pi over 2. Don't panic if you found the check questions hard. Just go away and do some consolidation work. There'll be plenty of examples to look at in your textbook too. It's really important that you do this follow-up work so that you're fluent with these topics, ready for when you need to build on them in FP2 or FP3. I hope you found this video useful. The next one introduces the exponential and natural logarithm functions. Goodbye.